Hello everyone, and welcome to our class in Artificial Intelligence and Machine Learning in Finance. In this video, I want to talk a little bit about some problems associated with classification trees and what can be done to improve on the predictive accuracy and the predictive performance of decision and classification trees. And as we've seen in the previous video, one problem associated with classification trees is overfitting. You can always use more levels, you can always use more nodes and go down even further, and what happens is the feature space is partitioned into more and more boxes, and this necessarily leads to overfitting. This is a problem for deep trees, while shallow trees obviously might underfit the data. In the previous video we saw an example where actually we only use two nodes, or three nodes actually, for partitioning the feature space, and this might lead to underfitting. So the variance bias trade-off is very important to consider in the context of classification trees. And one possible solution to this problem is to construct multiple different trees at training time and produce forecasts based on the mode of the classes in classification, or the mean or median of the response variable in the regression example of the individual trees. And this is an ensemble technique. This is called random forest. So what are random forests? They can be constructed by introducing sort of randomness into the construction of each tree. For example, if you choose random subsamples or variables and splits, and this will then yield trees that are built independently of each other. And this concept, this idea, is usually referred to as bagging, also bootstrap aggregating. Another approach is to use multiple trees in a so-called boosting framework, where we have weak learners. Those are the shallow trees, and they are combined to yield a stronger estimator, such that at each iteration step, classification or the regression error is reduced. And this will yield so-called boosted classification trees or regression trees, in which the individual trees are no longer built independently of each other. And to see an illustration, I would advise you, let me get my cursor, to watch these two YouTube videos. So this one is the first, and this one is the second. There, the principles of boosting and bagging are explained quite nicely, actually. And on the next slides, we will apply boosted decision trees to our classification problem, and we will rely on the XGBoost algorithm, which is quite famous in the context of boosting. So we want to fit a boosted decision tree. Again, carrot package. We do this in parallel for faster computation. 5-fold cross-validation. So this is train control. As we're fitting boosted decision trees, it's quite computationally intense. We only use 5-fold cross-validation. If you start the parallel computing session before that and you move this to a cluster, you can also try 10-fold cross-validation. SATC, as is tradition, and we have XTrain and XTest with the numeric data. So we again exclude all numeric features, all categorical features. The underlying XGBoost algorithm already uses parallel processing implicitly. Therefore, we only employ two parallel processes in caret, wrapped around the implicit parallelism that is included in XGBoost. So we set the tune length equal to 2, as caret selects 5 different parameters, and this will then lead to 2 taken to the 5th power different parameter combinations that are considered in cross-validation. So XGBoost model is our object. We train based on XTrain and YTrain. The method is XGBtree, so it's a classification tree that is boosted via XGBoost, and the rest is standard. Train control, TR control, our options, cross-validation 5-fold, and the metric used to select the best model is accuracy, and then we stop the cluster. So this is what we get out. 100 rounds, maximal depth is 2, and some additional parameters. And let's already consider the forecasting accuracy. So we predict based on XGBoost model. The new data is X test, the reference is Y test, and we look at the error matrix. And now we see that actually where we previously had, I think 170, we have an improvement compared to both the support vector machine and the unboosted classification tree. So the accuracy now increases to 97%, but most importantly, sensitivity increases. So it is a substantial improvement compared to the to all 3 previous models: the classification tree, support vector machine, and k-nearest neighbor. And you can see this in the increase in the sensitivity. It increased from 74 to 87% for the boosted tree ensemble. And by relying on the predictions from the boosted classification tree, for almost 300 out of the 341 customers, we can rightly predict that they are about to quit these services. This leads to the increase in sensitivity. And then the manager could act on this. On the other hand, we would falsely approach only 26 out of 1,725 existing customers. So yes, this could be a way to move forward. In the next video, we want to take the same approach, decision trees, but use it in the context of a regression analysis. We need to use different data. Why? Because now we need a metric response variable.